I put up the video yesterday on YouTube, and I sent it out in an announcement. So please let me know if you've had any trouble accessing that. Oh, that's weird. That's funny. I noticed that the count in the class went from 20 to 19. I was like, oh, someone's left already, but it was me. It was my tablet. Let me see. So I realized yesterday that I forgot to share a piece of research with you using econometrics to answer one of those questions you guys asked me about on the very first day, and that's embarrassing. I'm sorry about that. So this is another paper about the minimum wage. Minimum wage is probably one of the most studied features, questions that economists have looked at. So yesterday, on Monday, we looked at a way of studying it where in Denmark, if you are, the minimum wage basically kicks in when you turn 18. So we were looking at people that were just barely 18 and comparing them to people that were almost 18, and looking at the differences in their wages and then the differences in their employment, et cetera. This is a slightly different way of studying the same question, and this is just kind of a useful thing. So Seattle implemented higher and higher minimum wages over time. So in 2014, they made this decision to increase their minimum wage. It was implemented that there'd be an $11 minimum wage in Seattle in 2015, and then in 2016, the minimum wage went to $13 an hour in Seattle. So these authors are pretty cool, and what they did is Seattle's wages are here in the black line, okay? So you can see that they're kind of bouncing around, and then they go up and up and up as the minimum wage goes up. The blue line there is a synthetic Seattle. So what they did is they looked at other cities and counties in Washington, and they selected counties that when you added them together, they looked like Seattle in their trend. So that's why this blue line is moving right alongside the Seattle line. So it just means that this kind of fake Seattle that they've constructed looks like Seattle. It actually behaves like Seattle before the minimum wage takes effect. So you can see that the black line, Seattle's average wage, is going up relative to the synthetic Seattle. So that's kind of what the minimum wage is supposed to do. It's supposed to jack up wages. So here is the same kind of analysis, but for the number of jobs that there are. And so you can see that Seattle is actually having job shrinkage compared to its counterfactual, what would have happened without the minimum wage. That's what is going on over here on the right-hand side. So I can't point to it very easily on this figure. So then here's an interesting thing. So one is that you're less likely to have more jobs, to have jobs available. And then the second thing is, even if you have a job, you're actually going to have fewer hours because you're more expensive, because wages are increased. So here we have that the real Seattle employers in the real Seattle have to cut hours for their workers. So what that means is that in practice, payroll is actually going to decline in Seattle compared to its synthetic control, because while workers are being paid more per hour, they're less likely to have a job, and they're able to work fewer hours. So that's a really kind of an interesting, I mean, it's like exactly what you would think if you had taken an economics class, but it's a really nice design. It's a great design. So any questions about this, or about, let me take questions about this, and also questions about anything from yesterday or the day before, any questions you have on the homework or anything like that. Okay. Can someone just speak so I can make sure that I can hear you guys?
Low, low, low.
Awesome. Okay. Thanks, Warren. Okay. So today we're moving on and we are going to start talking about linear regression. So linear regression is kind of we call it a workhorse tool. It's like the tool that does most of the heavy lifting for economists. So simple linear regression, and it's heavily related to the stuff that we've already talked about, where basically we usually have a data set, something like, maybe the relationship between height and wages. And a regression is basically the way that we fit the line to the data. Okay, and the short story is that we're going to fit a line that minimizes the distance between the line and the points. We're going to try to fit a line that kind of goes among the middle of the points. That's intuitively what we're doing. It's not exactly that simple, but it will be a bit something similar to that. So how do we fit a regression line to the data? And how are we going to prove that that's the best line? That's what we'll be working on today. So sometimes we call simple regression, we call it ordinary least squares. And we'll talk about this again and again, but the idea is that we're going to remember that we have a regression equation like this. Xi, and then the u's are the distance between the lines, between our line and the data points. So what we're going to do is we will choose, what we want to do is choose, I don't know why this is being so fickle, choose beta naught and, oh bother. I deleted all this stuff. Beta naught, beta 1 to minimize the sum of the u's squared. So we're going to fit a line through the middle of the data so that it minimizes the distance between the line and each data point, that distance squared. So that's why we call it ordinary least squares. It's the line that minimizes the squared errors. So we'll go over how we estimate that, how we derive that estimation, how we interpret those, and then we might get to stated today, but I'm guessing we won't quite get that far. Okay. So here's just a generic way that we look at that we would model a regression. So it's just y as a function of x, and x is affecting y in a function that's a beta naught, so some intercept, plus beta 1 times x, where beta 1 is the slope of the relationship between x and y. And the way that we say this is that we're regressing y on x. So we're regressing the left-hand side on the right-hand side. We're regressing y onto x, where y, we sometimes call it the outcome variable. It's the thing that we think is affected by the x's, and x is the explanatory variable. The variation in x explains what happens to y. Beta naught, as we've said before, is the intercept. So it's where a line crosses the y-intercept. So say we had this point right here would be beta naught, and the slope of this line would be beta 1, if this were x and this were y. Okay, so we've got slope, and then the u is the error term. So say we had some data points, the u's are the distance between each of these data points and the line that we've selected. So I'll show you, we'll see all this again and again in different ways, but I'm just trying to give you multiple little doses. So I'm so irritated because I went through and deleted all of these before class. So here is, we're just going to jump right ahead to the formulas for calculating beta 1 and beta naught. Beta 1 is just going to be the covariance between x and y divided by the variance of x. So one way to think about this is that whenever we have a slope, the slope is rise over run. So in here we have the covariance between x and y is the rise in y for a change in x, and the run is the variance between x, the variance of x. So we're basically calculating the rise over the run by dividing the covariance between x and y, how much y changes for a change in x, divided by how much the x changes. It's going to help us calculate rise over run. So say we had a triangle, and this is the rise, the height is the rise, and the length is the run. To calculate the slope is just the rise divided by the run. The size of the height of the triangle divided by the length of the triangle. So that's for beta 1. To calculate beta naught, it's even simpler, but it's helpful to first have calculated beta 1. You can see that beta 1 is used to calculate beta naught. All you do is find the average y, subtract it from beta 1 times the average x, and that will actually give you your beta naught. And we'll see that in different ways in the next couple of slides. So remember that x bar and y bar are the mean of that variable. Whenever we have, e bar or x bar or y bar, that's always the average of x or the average of y. Okay, and yeah, remember that this beta naught is the y-intercept. And beta 1 is the slope. Okay, sorry. Okay, so we have 5 employment data for 5 people. Y is the hourly wage a person earns, and X is the number of years of experience they have. So we're going to be looking at the relationship between experience and earnings. And we're going to estimate the OLS regression line using this data right here. Okay, so all we're going to do is use our formulas from above. We've got beta 1 is equal to the covariance between x and y divided by the variance of x. And then the beta naught is much simpler, but we'll work on that. I just don't understand. I deleted all of this. So here's what the data look like. These points here are the data points. If we went back and we looked at this this data set, we'd find, okay, so there's a data point at 2, 1. So that's y equals 2, x equals 1. Let's go and plot that out. Y equals 2, x equals 1. So that one's right here. Okay, so you just plotted all of those points here on this scatter plot, and then I'm giving you a little cheat and showing you what exactly the line looks like. So the line's just going to go right through the middle of the points, and beta 1 is the slope, and beta naught is where the line crosses the y-intercept. So it's the intercept of the line. So I'm going to set this up with you, but we don't need to get too bogged down in the math for right now. So I'm going to give you the average x is 3. The average y is 5. And so first we're going to calculate the covariance between x and y, because remember that the beta 1 covariance x and y divided by the variance x. Okay, so first we got to calculate the covariance of x and y. So remember, our formula for that is right here. We're gonna multiply each x minus its average times its y times its minus its average, and we're going to add all of those products up and divide by n minus 1, where n is 5. So first we have the first data set, remember, was x equals 1, y equals 2. So we're going to calculate the distance between that x and its average multiplied by the distance of y and its average. It's going to give us 6. And then we're going to do the same thing for each of the other points. Okay, that's where we're getting -1, 0, 3, and 2. And we're going to divide by n, which is 5 minus 1, which gives us 4. So what we'll find is that the covariance between x and y is 10 divided by 4, which is just 2.5. So the top here, the top of our formula is going to be 2.5. Okay. Any questions there? Devin, Derek, Denelson, Cameron, Esmeralda, Katrina, Ibrahim, any questions there?
No, I think we're good.
Okay, awesome. So then to calculate the variance, of course, we have this formula that we've seen many times before. And so to calculate the variance, it's just each x minus its average squared, all divided by the sample size minus 1. So we're going to have 1 minus 3, 2 minus 3, 3 minus 3, 4 minus 3, 5 minus 3, all squared, and then divided by 5 minus 1. And that is also going to be 2.5. So in order to calculate beta 1, we'll divide the covariance between x and y by the variance of x. Both of those, we've just done the math, are 2.5. So beta 1 is 1.0, 1, just 1. Then we can plug this in. So remember that the formula for beta 1, the formula for beta naught is the average y minus beta 1 hat times x bar. So what's that? We have, let's see, y bar is 5. Oopsie. Y bar is 5. x bar is 3 and the beta 1 is -1. I'm sorry, is +1. And so that will give us 2. Beta naught is 2. Beta 1 is 1. Any questions there? Oh, we got some chats. Not at the moment. No question, no question, no questions. Okay. So the estimated regression line that we get is this right here. So whenever it's an estimated regression line, we put a little hat on top of the y. That means it's predicted or it's estimated. So that is our estimated regression line. And just like we calculated, we've got that beta naught is 2 and beta 1 is 1. So let's do some work together. This is can be really helpful because there are a couple things that can be confusing or tricky. So these questions will help us kind of iron out these things that are easy to get mixed up on. So what's the predicted value of y if x is 0? So the way that we do this is, remember, this is a predicted value, so we can use this formula up here. So the predicted value of y is going to be 2 plus 1 times 0. So that's going to be just 2. Okay. So that was easy. What's the predicted value of y when x is 10? So this is the same kind of problem, and we'll go, just plug in 10. 2 plus 1 times 10. That'll be 12. Okay. Is it possible for y to be 16 if x is equal to 10? What do you guys think? So let's first, we're going to calculate the predicted value. So predicted y is going to be 2 plus 1 times 10 is going to be equal to 12 again. So is it possible for y to be 16 if x is equal to 10? What do you guys think? Awesome. Okay. So this is a really good thing to do because this is a trick. So the predicted value can't be 16. But that's not what the question asks. So remember, notice that these questions ask, what is the predicted value of y? What is the predicted value of y? This says, is it possible for y to be 16 if x equals 10? So this isn't asking about the predicted value. This is asking about a data point in the world. Is it possible for y to be 16 if x is equal to 10? And the answer is yes. So I'm sorry, let me go to the blanker screen. Oopsie. Let me clear this out. Okay. So say we've got these data points down here, and there's an x equal to 10. And the question is, can we have a data point that's here at 16 when the line going through these guys predicts that it should instead, I'm going to use green for the prediction, it should be 12, that the predicted value is 12. So the answer is that the predicted value is 12, but it is possible that someone out there has 10 years of experience and is earning $16 an hour. So that's possible. Is it possible for y to be 16 if x is equal to 10? The answer here is yes. The answer would not would be no if the question said, is the predicted value exactly? Exactly. Yep. Very good question. Okay, so that's what we got. So the prediction using data is really nice, because say I give you one of these, a regression line, you can predict y if I give you x for people that aren't even in your data. It's very, very helpful sometimes. Any questions on that? I really want to make sure that I explain that clearly. Okay. So let's talk a little bit more about this. This is, so remember, this is our population regression line. We go out into the world and we estimate it with some data. So that's why it has a little hat on it. This hat is important. It tells us that this is a prediction from data. And then the predicted error is a really important feature of our regression. So the error is just how different is the actual y for each data point from the predicted y. Okay, so say we have this little data set here, and we've got our initial data are y and x's. So it's just raw information that we have from real people. And then using a regression, we're able to estimate the predicted value of each of those y's. So based on the regression line, what is the value of y on, usually when x is 1, we get 3. What's the predicted value of y when x is 2? 4. What's the predicted value when x is 3? We get 5, etc. Okay, so this is us plugging in x to the regression formula. Y hat equals something, 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 whatever that formula is, 2 plus 1 times x, for instance. Okay. So that's really important that we know where that comes from. So the predicted y is just plugging in x to the regression formula up here. So we just said, for instance, predicted y is 3 when we plug in 1 to this formula up here. We plug 1 into this formula. It's 4 when we plug in 2 to that formula. It's 5 when we plug in 3 to that formula. Okay, so then what is u? What is u? U is when we take the actual y and we subtract off the predicted y. So this is how far is each point, or is each point from the line, from the prediction. Okay. So all we're going to do here is y minus 3. So we get -1. 3 minus 5. So we get -2. 6 minus 7. So we get -1. Okay. So it's just a column that shows you how far the real data are from the predicted value. Okay. Let me stop for questions there, because that's a really important slide. Kimberly, Leanna, Levi, Manuel, Nev, Noah, Saul. Questions here? Okay, sounds good. Okay, so I'm going to show you two fascinating things about these U's. The distance between each data point and uh, and the prediction have two properties that are really interesting. So one, what is the mean of the errors? So we're going to sum up all these errors. We're going to get sum up -1 plus 2 minus 2 plus 2 minus 1. So what's that? We get these two will cancel out. -1 and -1 plus 2 will cancel out. So we'll get 0. So the mean of these is 0. Okay. So that you might think, oh, that's a special case that this is 0, but actually, whenever we do ordinary least squares, the sum of the error terms will be 0. The sum of the error terms will be 0. So why, I will show you in a little bit, but I'll just give you the idea that if we've got these points and the line goes through them, if they didn't sum to 0, this line would not go through the middle of those points. So the line that goes through the middle of the points, the errors will sum to 0. Okay. So then what's the covariance between X and U? So let's do that together really quick. Okay, so what's the mean of X here? Gotta find the mean of X. Okay, 1 plus 2 plus 3 plus 4 plus 5 divided by 5. That's 3, 3. This is 7 and 3, so it's 15 divided by 5 is 3. So X bar is equal to 3. Makes sense. Okay. So we're going to do the sum of 1 over n minus 1 times 1 minus 3 times u -1 plus 2 minus 3 times 2 plus 3 minus 3 times -2 plus, right here, the mean, we just learned that the mean u, so we're using this formula here, the mean u is always 0 and is 0 here. So that's why I'm just multiplying it by ui times 4 minus 3 times 2 plus 5 minus 3 times -1. So what is this? This is, the first one will be 2 plus -2 plus 0 plus 2 minus 2. Okay, so all divided by 4. And that's going to be, these will cancel out, these will cancel out, so it's just 0 divided by 4, which is 0. Okay, so the covariance between x and u is 0. So this is pretty cool. The mean of the errors is 0, and the covariance between x and u is 0. And the reason basically is that if either of these weren't true, the line would not go through the middle of the points. So any correct line that goes through the middle of the points is going to have a mean. The errors are going to have a mean of 0, and the x's are not going to be correlated with u. So that's pretty cool. Okay, but let me stop on that. That's important too. Any questions there? Did that make sense? I know that my stylus is not good. I got this 2 days ago, and it's not what I thought it was. It's like a stylus for like moving your tablet, like a fingertip. It's not a great stylus for writing, so I'm hoping that my other stylus gets here soon. But sorry that the writing's pretty bad. Okay. Let's see. Warren, Yesenia, Stephanie, Saul, Cameron, Denelson. Things okay over there? Okay. So I think you guys are fading pretty fast on this. So why don't we do some homework together? Let's take a little break and go take a 2 or 3 minute bathroom break, get a drink of water, and I will show you something fun, and then we'll do some homework. Okay. Okay. Let me share my screen really quick. My cousin sent this to me and I thought it was great. So I want to show you. Anyway, I thought that was so funny. The song is catchy, but
sing it.
anyway, the song's super catchy, but if you listen to the lyrics, you realize it's like a very shallow song. Oh yeah, the cougar guy looked tall. Dancers tend to be very short. I think it's a huge advantage to be short as a dancer. Cool. Let's do some homework. Let me just pause also. Any questions? You guys doing okay, hanging in there? Okay. Let me get some up here. Okay, can someone just say something so I know if my audio is working?
Hello.
Hello, perfect, thanks. Okay, so this is the same data as we were using before, but a different set of questions about it. So the first column is wages, the second is experience, And then the third column is a binary variable indicating whether or not an employee completed a training program. You can check your work with a calculator, but have to show how to set up the expressions, i.e. show your work. So the first question here is not too hard. The question is, what is the meaning of the variable training? So we've got this interesting variable here. I'm not sure that we've touched a variable exactly like this before. What do you notice about this variable? Cameron, Denelson, Derek, Devin, Esmeralda, what do you notice about the training variable?
A lot of people don't really have training.
Okay, good. So you got 2 steps ahead, a step ahead of me, which is perfect. So you said that most people don't have training, which is right. So one thing to notice is just that a 0 means that you don't have training, and that a 1 means that you do have training. So this is called a binary variable or a Boolean, and they're just used to describe things that are yes or no questions, or male or female, or black or non-black, or something like that in a data set. Okay, so you notice that most people don't have training. That's right. So the variable training says interpret this value in a sentence. So I would say that the training variable equals 1 if a worker has been trained. Yep, something like that. And the variable equals 0 if the worker has not been trained. So training equals 1 if the worker is trained, 0 if not. Okay. Okay. Any questions there? Let's see. Binary, yep. Okay. So does the data above suggest that training increases or decreases wages? Justify your answer using a specific example based on the idea of ceteris paribus from the data. So I think this is one that would be easy to be confused about. Ceteris paribus, what does ceteris paribus means? What does ceteris paribus mean, not means?
All else equal.
Perfect, all else equal. So what we're saying, what I'm asking for here is there's a specific example based on the idea of ceteris paribus in the data. So look at this guy, right? These 2 subjects right here. We have 2 people with 4 years of experience. One of them has training and the other doesn't. So we can use, so this is ceteris paribus, basically. One person is trained and the other isn't, but everything else in the data set on the explanatory side is equal. So we're going to use this comparison between these 2 to see whether it seems like training has a positive or negative effect on wages. So what do you notice comparing the trained person with 4 years of experience to the untrained person with 4 years of experience?
The person with training has a higher wage.
The person, that's right, the person with training has a higher wage even though they have the same level of experience. That's right. So I would say, does the above data suggest that training increase or decrease wages? I would say it seems to increase wages because 2 people have the exact same experience but different levels of training, and the person with training is earning $4 or 1/3 more than the person without training. Okay. Let's see, there's a question in chat. All else equal, good. Any questions about that? So the ceteris paribus idea is really key to econometrics. We're always looking to compare people that seem to be the same in every other regard, except for the thing that we're trying to measure. So those Seattle pictures that we just saw at the beginning of this lecture, where it like makes us feel good that the employment and the wages are tracking one another before the minimum wage is implemented, but they're differing only after the minimum wage is implemented. That makes us feel like the comparison group is the same, this ceteris paribus in every other regard. It's a very kind of key feature of what economists are trying to do, is find comparable people or comparable firms or comparable countries that had different exposures to some sort of treatment that we're interested in studying the effect of. Any questions on B? So what's the covariance between wages and training? So this is, let's remember what so the covariance between wages and training is equal to 1 over n minus 1 times the sum of Wi minus W bar times training I minus training bar. Okay. So does anyone have handy what the average wage was? What was wage? What was W bar? And we'll calculate training bar. I don't have it
It
handy.
was 13.3.
13.3. Awesome. And then does anyone have T-bar? What's the average amount of training? So T-bar is going to be 1 plus 1 plus 0 plus 0 plus 0 plus 0, all divided by 6, which will be 0.3, 1/3. Okay. So I'm just adding up all the T's and dividing by the number of observations that we have. Okay. So let's do that together. Let me pull out a spreadsheet. I can do my work in 13.3. Absolutely right. Okay. So remember the covariance, what the covariance is doing is basically saying when we have values of X that are higher than average, do we tend to have values of Y that are higher than average or lower than average? So if positive covariance will be that when we get big X's, we get big Y's. A negative covariance is when we have big X's, we have small Y's. Okay, does anyone calculate? Like that's, let's see. Let me just do one little thing here. Okay. So I get, has anyone else gotten an answer on this? So I get a covariance of between wages and training of point of 0.66666. What does that suggest about the relationship between these two variables? It means that they're positively related. They're positively correlated. Positively covariate. When you get a large value of X, you tend to get a large value of Y. So you can see that a little bit in the data. It's not actually super clear to me without doing the math, but we have these two folks down here with training, and they are both earning kind of at the higher end of the distribution, with the exception of this fella who's earning $20 an hour. But other than $20 an hour, man, the trained people all earn more than the untrained people. So it kind of makes sense. What does this suggest about the relationship between the two variables? It suggests that people with more training tend to earn higher wages. Okay, cool. Yesenia, thank you for checking me. Appreciate that. Okay. What does it suggest? It suggests that they're positively related. Okay, is your answer to part C consistent with your answer to part B? So what do you guys think? Is our answer to C that there's a positive covariance consistent with our answer to part B? Yeah, I'd say that they're consistent with one another for sure. Why are they consistent? Well, we find in B that people with more training but equal levels of experience earn more. And we also find that covariance suggests that also people that have more training earn more. That makes sense. Those are the same. Cool. Well, that was easy. Not too bad. So this one, today is Wednesday. If I make it due Friday at midnight, is that okay? Okay, awesome. The last class I taught, they said that they wanted more homework. So I was like, okay, we can do that. We can just make sure that we've got enough homework going on. Because it is nice to have practice and to have kind of exposure to the material in this form. So that's good. Okay. Do you guys want to go back and do some more OLS? Or would you like a break for the rest of today and then we'll resume tomorrow? We can do either. Resume tomorrow. Okay. Any other feelings? Don't mind OLS. Cool. How about this? I just feel bad because it's only 11:20. So why don't I go for another 5 minutes or so? We'll just get one more thing. We'll just get one more little part. I just think it's good to break it up and get through a little bit more today. So this homework is due Friday at midnight, right? Yes, that's exactly right. Okay. We're on a roll. We're on a roll. Let's see. So now we know how to estimate a linear regression. We need to see where our equations for beta naught and beta 1 come from. So we might not get all the way through this. This takes a little bit of time, but we'll make it the first pass. Okay. So first, we're going to do a little bit of, I think all of you have taken calculus before. And if not, that's totally okay. You really don't need it for this class too heavily. So I think I can teach you everything that you need to know about it. So if we have a function like this, where there's a function within a function, like a Russian doll is a small doll and a larger doll. So this is a Russian doll function where we have a small function and a bigger function. And we're taking the derivative. So remember, whenever we take the derivative, what we're doing is we're finding a function that describes the slope of a variable. So say we had a function like this, and there was a line, and it was a straight line. If we took the derivative, of this line, we would find that it was just a single number like 2, where 2 is the slope of that line everywhere. And the function is just 2, the derivative is just 2 because its slope is constant, its slope never changes. If we had a slightly different figure where the slope changed a little bit like a parabola, we'd find the derivative would be a function that would describe how that slope is changing over time. So the derivative function would be something like, the derivative would be high, and then it would actually be 0, and then it would go negative. Why is that? Because first, the slope over here, there's a positive slope. So that's why we have positive numbers. Here, there's a 0 slope. That's why it crosses 0. And here we have a negative slope. So that's why the values are, the values are negative. Oh gosh. And I should just correct one little thing, which is that this line is actually probably constant. So that's why we have negative values over here. So derivative just describes the slope of a function. So when we were trying to find the slope of this fancy function right here, we first take the derivative of the outside part of the function, the f. F prime means that we're taking the derivative of the outside, and then we multiply that by the derivative of the inside of the function. So that sounds scary, but it's not. So as an example, here we have a function, and we can see that there's a square here. So this is the outside of the function. The f of the function is that we're squaring something, and the inside of the function is that we have 3 times x plus 5. So first, we're going to take the derivative of the outside. And remember, when we take the derivative of the outside, we're just taking the exponent down and subtracting 1 from the exponent. So we get 2. times 3x plus 5. And then we're going to take the derivative of the inside of the function right here and multiply this whole thing by the derivative. So the derivative of this inside is just 3. That's where we get this guy right there. Okay. So all we have is the derivative will be 6 times all times 3x plus 5. So it's the derivative function. So don't worry about that. I'm not gonna make you do too much with that. So sorry. So basically, to find what line is going to minimize the distance, the square distance between the points and the line, we can use calculus. And in fact, that's how we do it. So the homework is due this Friday at midnight, right? Yes, that's correct. So I'll put it up online as soon as our class is over. So what we're going to find are the solution to the minimization problem. It will give us beta 1 is equal to the covariance of x and y over variance of x, and that the beta naught is equal to this right here. So what we're trying to do implicitly is find beta naught, beta 1 that minimizes the sum of the errors squared. We're trying to find betas that minimize the distance between the data points and the regression line. Okay. So the way that we do that is going to look really simple, really intuitive, I hope. So, and remember here that the beta naught is the intercept and beta 1 is the slope parameter of the line that we're estimating. And these u's are so important. The u's are just the distance between the data point itself and the predicted line. And we're trying to find predicted lines that minimize the square of these u's. Why is it the square of the u's and not the u's themselves? The short answer is that it's much easier to work with a squared term instead of a linear term. It's much easier to do calculus with a squared term because everything is smooth. When you have linear terms, it's much more complicated because you don't. So smoothness, I know this is a little tangent, but smoothness is very useful. So say we had a function, and the function was like this. So it's not smooth, it's going to minimize somewhere, but there's nothing smooth about it. It's actually quite hard for a computer to find the minimum here because you can't use calculus, you have to use a search function. Calculus is wonderful because all I have to do to find the minimum is take the derivative and set the derivative equal to 0, because where the derivative is equal to 0, that's the minimum. Where the derivative equals 0 is the minimum. Okay, because we're minimizing sum of squared errors, okay? So notice this function over here, this v doesn't have a 0 derivative anywhere. It has a positive derivative here and a negative derivative here, and there's actually no derivative right here. There's nothing there that we can get because it's not a smooth function. So that's why the squares are so nice, is that they're gonna be able to give us, to tell us right where the minimum is. Okay. If that doesn't totally make sense, it's okay. It's just a useful thing for someone that has taken some math. It will help it click for them. the goal is to choose a line that minimizes the sum of the squared errors. So the sum of the squared errors is simple. It's just the square of u1 plus the square of u2 plus the square of u3 plus the square of u4 plus the square of u5. And note that from this function, we can actually find a nice expression of u that's in terms of beta 1 and beta naught, the numbers that we're trying to derive. So ui is actually equal to the yi minus beta naught minus beta 1 times x. So that's going to be very useful because instead of minimizing, we were going to try to minimize this, and we'll be able to substitute for u u squared is equal to yi minus beta naught minus beta 1 x. So that's going to be very useful for us because we're going to be able to use this function to take the derivative with respect to our choice variables, beta naught and beta 1. That's where we're headed. We're trying to minimize the sum of squared errors. I'm repeating myself in part because this is just, it doesn't click. If it doesn't click right away, I'm trying to find different ways of trying to convey the same idea. So we're trying we want to find the line that is the choice of beta naught and beta 1 that minimize the sum of squared errors. We're going to notice that this u term can be substituted with yi minus beta naught minus beta 1 x. And that's going to be very useful because we can take the derivative of this function with respect first to beta naught. We're going to get a function that looks like this. So when we take the derivative, we're going to take the exponent and bring it down. That's where this -2 comes from. And then the derivative of the inside with respect to beta naught is -1. There's just a -1 invisibly right here. That's why we have -2 in front. And then, so that's one equality that we'll be able to use. This is the first equality we'll be able to, that is going to help us. So this, we're going to choose beta 1 and beta naught to satisfy this equation right here. So that's our first condition. Our second derivative, and that's not really a second derivative, our second first order condition is that we're taking again the derivative. So we have to, that's why we have to take down this 2 from the exponent. But now, because we're taking the derivative with respect to beta 1, we need to take the derivative of the inside with respect to beta 1, which is going to be -x1. So that's why we have an x right here and the negative right there. Okay, so that these are our 2 clues, basically. We're going to take a first order condition with respect to each, the beta naught and the beta 1. And why are these clues? They're clues because the beta naught and the beta 1 that we choose have to satisfy both of these equations. So now what we have are 2 equations and 2 unknowns, beta 1 and beta naught. And we can use, when we have 2 unknowns and 2 equations, we can use the equations to solve for the unknowns. So this is important. It is easy for this to not click right away, I think. This took me a little bit of time when I was in this class to kind of let it sink into through my skull. It just took some time of looking at it and thinking about it and hearing it and reading it. So let me pause and just make sure and hear your questions for this for right now. And we'll go through this again on tomorrow. Okay. Okay, sounds good. So we will resume tomorrow. You guys are doing great. And yeah, well, you're welcome to go, and I will hang back and answer questions. Oh, good. I'm glad to hear that. My pleasure, Stephanie. Thanks.